Good morning, ladies and gentlemen. This is Sang-il Park. I'm the founder and CEO of Park Systems. It is a great honor to have this opportunity to present my talk, Unraveling the History of Atomic Force Microscopy, the Genesis and Evolution of AFM from Laboratory Instruments to Industrial Nanometrology. This is my own story over the last 40 years. I'll begin with the invention and commercialization of SPM and explain how we innovated the AFM technology to make it more accurate and more user-friendly, followed by applications and future perspectives. It was 1982 when I joined Stanford University as a graduate student and met Professor Kelvin Quate. And that's the year when the first STM image of a silicon atom was revealed, was acquired. It was really a fascinating image. And Professor Quate started a new project in this field, and I joined. After joining the group, I built my own STM, scanning tunneling microscope in ultra vacuum, and tried to reproduce silicon 7x7 image, but that was not easy. It took lots of effort, patience, and some lucks. And one day, I finally got nice 7x7 image. I was so happy. And I was even more luckier that the instrument I built appeared on the front cover page of Physics Today. So I was very happy. Around that time, Professor Quate invited Gold Binnick and Chris Gerber for their sabbatical at Stanford University. And we were discussing how to enhance the capability of STM so that it can image any samples regardless of electrical conductivity. And one day, Gold Binnick came up with the idea and AFM was invented. Binnick's idea was to insert a tiny gold foil with a diamond tip between the sample and the STM tip. It was a simple and elegant idea, but not that practical. It's hard to make a nice image with this setup. Later, people came up with many ideas, and finally, the tunneling tip was replaced by micro-machined cantilever, and STM tunneling was replaced by beam bounce mechanism, which works quite well. So now AFM became a practical instrument with commercial and commercially viable. So I saw business opportunity. Let's start a company, AFM company. So I started my first company, Park Scientific Instrument, in 1988. And we launched the first commercial AFM in 1990. And we were the sole source of probes. So even our competitors had to purchase probes from us. And I was generous enough to supply to all of them, and I thought that was a fair business. In early days, besides Park Scientific Instrument, there was topometrics and digital instrument. And after spending 15 years in the US, I thought I should go back to my home country. So I sold the company to some group and came back to Korea, starting my second company. Initial name was PSIA. We changed the name to Park Systems. In the meanwhile, Topometrics was also acquired by Thermo Group to form Thermo Microscope. And Vico Metrology acquired the digital instrument, and later they acquired Thermo Microscope as well. So Vico, they got all three major companies for a while, so they enjoyed their business. And later, Bruker acquired Vico Metrology. Shortly after Vico acquired the digital instrument, a few people left the company and formed Asylum Research. And later, Oxford Instruments acquired Asylum. There are many other companies. For example, Seiko Instrument was one of the major players in Japan. Later, Hitachi High-Tech acquired them. And molecular imaging was famous for liquid imaging. And they sold the company to Agilent. They changed the name to Keysight, but discontinued AFM business. As I said, my second company was founded in 1997. And we went public in 2015 at KOSDAQ, Korea Stock Exchange. And currently, our yearly revenue is about $150 million US. And there are about 500 people, full-time employees at Park Systems worldwide. And our market capitalization is about $1 billion US. This is our growth curve. Since IPO, we grew about 30% every year. And our stock price went up about 20 times since IPO. So we grew faster than other AFM companies. In particular, in the year 2022, our revenue, AFM revenue, surpassed that of Bruker, the long-time leader in AFM. So now we secured market share #1 position, followed by Bruker and Oxford. So how did we achieve this success? The answer lies in continuous innovation in AFM technology. Let me walk you through the detail. This is the principle of AFM, which I don't have to explain to you the detail. But the original AFM started with this tube scanner based, and that was the start of the problem. The first drawback is image distortion. Tube scanner rely on its bending motion for its X and Y positioning, so it has inherently distortion out of a plane curvature motion and crosstalk between axes. So flat surface does not look flat. In order to address this problem, we restructured the AFM, separating XY scanner so that it can scan sample in horizontal plane only, and having another scanner to move the probe in vertical direction only. Both X, Y, and G scanner has a stacked piezo actuator, and it has flexure hinges. Once it is well engineered, we can make it very flat scan. This is 80 by 80 micrometer optical flat scan. It's within 1 nanometer range. And it has a very good linearity and orthogonality. We optimized the sensor and servo mechanism. So flat XY scanner produce distortion-free image, and fast G scanner opened the possibility of achieving true non-contact mode. This is an example of how the new scan system can achieve. This is an image of a faulty recession. In hard disk industry, measuring PTR is an extremely important task. Relative to air bearing surface, the read-write pole are slightly recessed, and it's important to measure such numbers very repeatably. very accurately. It's very challenging because the reference plane is quite far away, 10, 20 micrometers away, while the PTR itself is only 1 to 2 nanometer. And the 1 sigma repairability is 0.01 or 0.02 nanometers. Very small numbers. It is not achievable with the conventional tube scanner-based AFM. Another problem is tip wear. As the tip taps into the sample surface, tip gets blunt, and it cannot reach into the narrow valley, and the RMS roughness value drops as the tip radius increases. This is a problem. So why did tapping mode become so popular from the beginning? Well, it was not the tapping mode people aimed. They tried to make non-contact mode, but they compromised with the tapping mode. The original idea of non-contact mode is oscillator cantilever near its resonance frequency, where the slope is at its maximum. And then approach to the sample. Then due to the van der Waals attractive force, the amplitude would, the resonance frequency would shift downward and the amplitude would drop. And now we want to maintain this amplitude and scan laterally. The difficulty is tip sample interaction is not monotonic. The amplitude drops linearly until a certain point, but at the mode hopping point, the amplitude suddenly jump up and drop. Now, tip sample interaction is becoming into a repulsive mode, tapping mode. And even though they withdraw the tip, it remains in tapping mode for a while, and then jump back to non-contact mode. So there are bistable regions. It makes the solver very challenging and difficult. Well, some people found there is an easy solution. Instead of using right side of the resonance frequency, if they use left side, lower frequency than F0, then the simple tip sample interaction becomes monotonic. Even the attractive force make the amplitude goes up and then gradual attenuation. Very error tolerating mode. So tapping mode was an easy solution, but it came at the cost of a tip wear. In order to achieve non-contact mode stably, we have to achieve a stable system with a low noise system, optically and electrically, and remain in this small range, plus minus 1 nanometer in amplitude, plus minus 2 nanometer in Z. So a low noise, fast Z solver is the key. This is an example of tip wearing. The sample is chromium nitride tip check sample, which is very sharp and abrasive. In tapping mode, in few scan, few images, tip gets blunt and emoji get blurry. Whereas non-contact mode, the chip remains sharp even after 100 scan. This is estimated tip diameter, repeated a number of repeat scan. This is an extreme example. We imaged polished silicon 15,000 times, 15,000 images over 3 days, 10-hour scan. And the RMS roughness value remains the same. The non-contact mode has many merits. One of them is capable of measuring soft samples like unbaked photoresist. This is a 5 micrometer scan of PR, which was previously examined with SEM, 2 micrometer and 1 micrometer scan. And we can see the damage from the electron beam. We even studied the relationship between the E-beam irradiation current and shrinkage, both in width and height. But in early days, maintaining the non-contact mode was not easy, even to us. So we studied how to optimize the G-ball server system so that you can improve. This is the AFM system, and this is a model of AFM system with the classical control theory. Here the H is the sample height. This is the input, and G output is the G scanner, and the difference because produce error signal, and this error signal is processed with sensor transfer function, controller transfer function, and system transfer function, and generate the output Z. And the open loop transfer function is defined by Z over E, right? This is the input, this is the output. The closed loop transfer function is Z over H, right? And in order to make an ideal AFM, we want to make the closed loop transfer function behave like a low-pass filter. Stay one for a while and then gradually attenuate if the frequency goes up. And for that purpose, if we calculate the relationship, we found the open loop transfer function should be like a simple integrator, like this. If we study the each transfer function, the system transfer function is dominated by the mechanical response of a scanner, G scanner. It has 9 kilohertz resonance frequency with a quality factor of 5, giving us an effective bandwidth of 5 kilohertz at 3 dB, pretty high. And the sensor transfer function for non-contact or tapping mode, it has a low pass, it behaves like a low pass filter with a typical bandwidth of B defined by this equation. The detection time constant, because of the settling time of the cantilever, 2 times Q over omega 0, is pretty slow. For typical cantilever, having 300 kilohertz resonance frequency, it has about 600 hertz bandwidth, pretty slow. Even for small high-frequency cantilever, the detection bandwidth is only 2-3 kilohertz at the most. So you cannot scan much faster than that. Controller transfer function has a professional gain and integral gain, and a ratio defines crossover frequency omega c. Now, it is important to match pole zero. What I mean is, this frequency is relatively higher, so we want to make this B matching with controller 0, omega c. Once we make that, then open loop transfer function is close to simple integrator because P is quite flat with a much higher frequency kink. Then now open loop transfer function is more or less a simple integrator, and closed loop transfer function is what is desirable. If the pole zero is not matched, then the tip, the G scanner, cannot follow sample geometry precisely, as shown in this simulation result. After the pole zero is matched, we have to optimize the total servo gain. If the gain is too low, it becomes too slow, and if the gain is too high, exceed 1, then it starts to oscillate. So we have to make H, closed loop transfer function, remain close to 1 as much as possible, but not exceeding it. For that purpose, faster G-solver response, high resonance frequency of G-scanner, and lower quality factor is desirable. Now we have optimized the G-solver control. Then what would be the optimal lateral scan speed? Earlier, I explained that open loop transfer function, which is Z over E, should be a simple integrator. There is a clue. This means the topographic signal, Z, is more or less some constant times time integration of error signal. And if we differentiate this, then dz over dt equals gain times error. dz over dt is simply vertical speed. If there is a given sample slope, then this vertical speed is scan speed, lateral scan speed times slope. This is a very simple but important formula. Scan speed times slope equals gain times error. Well, sample slope is given, and once you optimize the gain, then scan speed is just proportional to error. If you scan faster, you generate more error. That's it. So by using this characteristic, we can optimize the lateral scan speed. We call it adaptive scan using previous line. The first scan have to be slow because it's unknown territory, so we conservatively get the first line. But once we get the first line, we can estimate the next line, which will be close to each other, because the line spacing is much smaller than typical topographic variation, as you can see here. So for example, from this line, 107th line, we can estimate what the next line will be, and then program the scan speed. Well, we scan faster in this flat region, and we slow down when there is a steep slope. That's the idea, using this formula. So adaptive scan has a good advantage. In adaptive scan, it took 227 seconds with a pretty good matching. Forward, backward scan line matches pretty well. In order to achieve such error signal, we have to scan much slower at fixed rate scan speed, more than 1,000 seconds. But here, we can scan faster than 1 Hz, producing much less error signal. So now, the user doesn't need to adjust the gain or scan speed. They just tell how fast I want to scan. If they increase the error toleration from 0.2 nanometer to 1.5, then it can scan faster. So the UI is now different. If it is a draft mode, then we sacrifice the accuracy and speed the throughput, scan faster. If you want to get the most accurate data, then you put higher priority on accuracy and spend more time. So now all the operating parameters of non-contact mode are optimized, such as operating frequency, set point, integral gain, proportional gain ratio, overall gain, and scan speed, etc. Then let's automate the hardware as well. The pain point in using AFM, there are many pain points. The first one is change no probe. Tip exchange is frustrating even for veteran users, causing up to 50% cantilever breakage, according to Dalia Yablon. Read her article. After 30 plus years, AFM can be still frustrating to use. In order to answer this request, we pre-mounted the cantilever chips on chip carrier. This is the mounting station. It's automatically mounted. And this chip carrier has a QR code containing serial number, probe type, and all other statistics. And this probe mount carrier chip is attached in this kinematic hand, probe hand, having a magnet at the center and 3 balls. And our system, our latest AFM, has a QR code reader and automatic exchange module. And once the QR code reads the QR code, you can select one of the 8 probes on ATX module. Then the AFM head goes down and pick up the chosen probe. Depending on the strong magnet underneath, where it is at the center or is far away, the probe can be either picked up or parked. Another difficulty in using AFM is align the laser beam. Sometimes it is hard where the laser beam is, and you have to manually adjust to align the laser beam at the center of a cantilever. And the reflected beam have to sit to hit the center of PSPD, and you have to adjust all those manually. So one need a trained operator to use AFM and get good image. So in order to make it automatic, we designed a new optics stage. This optics stage now is sitting on optical XY stage. So this whole optics can move in X and Y direction for a millimeter or so. And the laser or SLD, super luminescence diode, is fiber coupled and feeds through in this optical microscope, and it is focused through this objective lens and hit the cantilever. So we designed such that this laser beam is at the center of vision, optical vision, all the times. And from the camera, the motion vision finds out the cantilever position and moves optic stage so that this cantilever end is centered where the SLD beam is. And the reflected beam is adjusted by this setting mirror with 2 motors inside this AFM head. So beam alignment is all done automatically. Another difficulty is sample navigation. You know, sometimes it's not easy to find the area of interest, and it's even more challenging if you want to go back to the same position after sample remount. So we used kinematic mount sample chucks. There's a magnet and sample disk, 4 of them. And then it has a sample view camera. This is the captured image of a sample view. So just you click a mouse, then it reads the XY coordinate, and the stage goes there. And you can get back to the same position repeatedly. So with all those improvements, we designed FX40. This was the dream machine project, creating ultimate AFM for maximum convenience, automatic probe exchange, automatic beam alignment, optimizing the G-servo and sample navigation, and higher performance, having a low noise floor. I didn't tell the mechanical advantage of details, but it has a much significantly lower noise flow and high resolution and less thermal drift. and it has also additional features such as self-diagnostics and environmental sensing, temperature, humidity, oscillation, vibration, tilt, and acoustic noise, and so on. There is an introductory video on YouTube. Now the view is exceeded 1 million. If you have not watched, please take a look. And also, there is an actual system at the exhibition, so please come and take a closer look. We also developed industrial AFMs for semiconductor fabs by adding 300mm wafer handling systems, SEX-JAM communication protocols, and automatic navigation, and environmental control. In semiconductor industry, they use AFM for front end, such as surface roughness measurement, height, depth, width, angle measurement, CMP metrology, wafer edge metrology, defect review, and electric conductivities. For the back end, they measure copper pad height, redistribution layer metrology, and more. It's expanding. Now, this back end advanced packaging is a really hot topic in semiconductor industry. In particular, EUV mask use our AFM to review the defects and repair. Let me show you some applications. This is phase shift apodization mask, a crucial component for coronagraph for space telescope. So our non-contact mode can measure or image a relatively large structure like this very accurately and precisely. Our non-contact mode AFM can also image tall samples like deep holes, high pillars. This is for nano imprints. The depth is about 6 micrometer. These are a high resolution example of high resolution AFM images showing 2D molecular networks of melamine and cyanuric acid formed on HOPG. And as we zoom in, we can see moray patterns, and finally, molecular network images, where the lattice period is about 0.98 nanometer. The molecular structure of this sample is more clearly visible using conductive AFM. Previously, only STM was able to show such detail, but now our conductive AFM shows equally remarkable images. Graphene on hexagonal boron nitride is another intriguing example. Depending on the orientation of graphene relative to hexagonal boron nitride, there are different moray patterns generated. All conductive images are. This is a similar sample, but this time there is a double layer, twisted bilayer of graphene on top of a hexagonal boron nitride, 30 nanometer thick. And this is similar to previous one, but on top of this double layer, there is a very peculiar phenomena happening. This is all current image, not real topography. So we don't quite understand the nature of this phenomena, but Professor Tomoki Machida at the University of Tokyo is currently studying this topic. With contact resonance piezo force microscopy, we can observe beautiful patterns of tiny lateral piezo response on twisted bilayers of a hexagonal boron nitride. It's a marginally twisted, very small angle. For a bio application, I picked this image of a DNA origami. This AFM image clearly shows the DNA strands folded into a rectangular shape, closely matching the truth tile schematic. Let me show you some semiconductor applications. First, this is an image of ultra-flat silicon wafers, 300 millimeter bare wafers. The roughness is very small, 0.067 nanometer, and it changes slightly depending on the position. And more importantly, we have to generate consistent measurement numbers. Dynamic repeatability is 3 sigma number is below 0.003 nanometer. By measuring multiple site points, we can generate the roughness map of the entire 300 millimeter wafer, and we can study the radial variation depending on the roughness. AFM is an excellent tool for micro-lens characterization in CMOS image sensor. It can measure width, intervals, pitch, height, and radius of curvature very well. This is an example of a narrow trench metrology having 16 nanometer CD and 35 nanometer depth. And we can also observe the line edge roughness. This is not a noise, imaging noise. It's a real feature. Sidewall roughness is better measured with the 3D AFM, our unique AFM, where the head is rotated 38 degrees, so the tip can image this sidewall as well as floor or top very well. And we can see, depending on the exposure tool, the sidewall roughness changes a lot. CMP metrology is another important area for AFM, or atomic force profiling, long-range profiling. In this case, it shows this edge over erosion phenomena. AFM is also used for electrical failure analysis in automatic 300 millimeter system. On a defective contact, this IV curve has a different characteristic, and we can see there is a leakage current at 4 volt plus 4 volt at 5 nanoampere. And that is coming from excessive size of the P well underneath. Here the challenge is locating the AFM probe right at this contact, metal contact. Imaging is easier, but going back to this contact is not that easy because it's small area scan, 250 nanometer scan. So the drift can affect and other things can cause problem. Measuring copper pad height for wafer-to-wafer bonding is increasingly important application. And like a PTR, which I showed earlier, this is wide scan, quite far away, but this vertical variation is order of nanometers. So it is not easy to measure such height changes with other tools. Only AFM can provide such nice tool, nice measurements. Our AFM can be used for defect review on wafers and photomask. This is an example of photomask. We can see some particles and pits. AFM can also remove the particles. There is a defect as shown in transmitted optical image, and it is reviewed by SEM and AFM. And then by brushing with the AFM probe, we successfully removed. AFM can repair hard defect as well, bridge type in this case. So by scrubbing this bridge with AFM tip, we were able to remove. Well, we used different probes for repairing and imaging. Future perspective, well, AFM has advanced significantly, but I can see the AFM can be better. For higher throughput and more user convenience. And AFM can be combined with other tools like interferometry, holography, ellipsometry, and nano-IR, and more, and complement each other and produce hybrid metrology solution. So in summary, 40 years of innovation has transformed AFM from a laboratory instrument into a widely used commodity instrument and critical metrology tools in the semiconductor fabs. Park Systems led with continuous technological advancements, flexure-based orthogonal scan system, true non-contact mode, optimized the server system, automated operations. More advanced AFM solution will come from Park Systems. Thank you very much for your attention.